There are base units and derived units. Much of the things we calculate are derived units. There are scalars and there are vectors. And again, much of the things that we calculate are vectors. And you'll see that velocity is calculated one way, and that acceleration is based on velocity, that force is based upon acceleration, and that energy in all its forms and all the different equations is related to force. So I hope that by putting all these materials together that I will simplify your understanding, increase your ability to see the connections and relationships between these different pieces of math, and hopefully by integrating it properly will allow you to do better in the course. So forgive me if some of this seems familiar and if some seems unfamiliar, but this rearrangement, I hope, is going to be for your benefit. So previously we saw this page on page 6 of our text, the very first section, matter and energy. We've got this wheel, and the wheel allows us to make the point that we're looking at forms of matter that are powered by energy. And the matter piece is quite familiar to us. We see solids and we see liquids. Perhaps we imagine that the wheel is metal and the brown chute is wood, and then of course the liquid is probably water. We ask, what are the solids? We ask, what are the liquids? And we ask, well, are there other forms of matter present? And probably based upon your past experience and other coursework, solid, liquids, you guess the other form of matter is gases. And so when we did this in class, it seemed like there was a great deal of understanding of the matter. But energy is different. The questions we ask about energy are always different because we don't directly observe energy the way we directly observe matter. Matter, we can detect it with our senses. We can hold it, we can feel it, we can see it. But energy, we don't actually directly see. Instead, we see the effects of energy. And so these questions are actually mysterious, especially with the question of what is the energy's direction and how does it flow? What does it mean to even say energy? Our answers to these questions show that energy in the different forms it takes is a much more challenging topic. Now, a major difficulty emerges when we attempt to talk about things like energy. In everyday life, people use words like force, energy, or power in a casual way as if they all mean the same thing. But they don't. To make sense of how everyday matter interacts with energy, we need a clear understanding of how energy is related to these other ideas in the physical sciences. And to do that, we may need to jump around in whatever text we're using. Here you see that this was some information from page 6 of our text. So I'm jumping to page 36, which is a completely different chapter, almost a completely different section away. Vectors and scalars. A scalar is simply a property, a mathematical property, a number, if you like, that has a scale. That is, it's either big or small. We talk about its magnitude, we talk about its size. You can say different words, but that's what we're interested in. It's the size of the number, how big, how small. Scalars only have that property. And many properties of matter are scalar, and so much of the numbers we measure and record in lab are scalars as well. So the volume of a solution in milliliters, as in our most recent activity where we formed strontium carbonate, or the mass of a substance in grams, which we have done in each of the last 2 labs. We've measured substances in grams. Well, both the volume and the mass of a substance, these are simply numbers that tell you how much you have. They're scalars. But some quantities are said to be vectors. And a vector is something that doesn't just have magnitude, it has direction. It's going in a particular direction. To illustrate that, we have the Olympic sport of curling. It's played on ice. People have skates. And members of a curling team will attempt to move a large disc called the stone. It's heavy. It's made of granite. And the idea is to get it moving at just the right speed so that it will slide on the ice and it will eventually come to land in the desired target, which is called the house. Very popular in Canada and North America, the sport of curling. We're going to use this to illustrate a lot of ideas, a lot of basic ideas in physics and chemistry. So in this case, a curling stone is made of 20 kilograms of granite. It's directed with a velocity of 4 meters per second toward a target called the house. Whee! There it goes. Now, in this example, the question students should ask is, which of these properties described has only magnitude and thus is a scalar? And which property having both magnitude and direction is a vector? Well, the curling stone's mass is simply a number, and it doesn't appear to change based on whether it's at rest or moving in a particular direction. The mass of the stone, 20 kilograms, is a scalar. It simply tells you how big the stone is. But the velocity is a number that has a size, and it's changing in a particular direction towards the house. Since velocity includes direction, it is considered to be a vector. Now you might say, well, how big of a difference does this make? Notice I've got a railroad train going by, and it's shaking a sign. And on one side of the sign, highlighted in blue, we have scalars. The other side of the sign, we have vectors highlighted in red. And you'll see the word speed, and you'll see the word velocity. Well, in everyday life, people use those words like they mean the same thing. And what I'm going to show you is that the effect of a unit having both magnitude and direction is subtle, but it's a very important difference. We consider this train. It's moving. We imagine it's moving on a circular track. We can't see that right now because we're looking at it only from one angle, but let's say it's moving on a circular track. And let's say further that it's moving with a constant speed, the speed being 4 meters. Now, what that means is that no matter which direction the train is moving at on that particular moment, no matter where it is on that circular track, whether it's facing north or west or east or south, it doesn't really matter. Its speed is essentially 4 meters per second. The speed is constant. But now let's look at this setup from a different perspective. Here we can see that the track is curved. And what we realize now is that this can't be a constant velocity because the velocity has a particular direction. So the velocity must be changing at every moment. The speed here is constant, but the velocity is not. And therefore, speed and velocity are not, contrary to common usage, the same thing. They are different things, subtle, related, but different. As a further example of this distinction between speed and velocity, we have ants on a Mobius strip. And you can see that they're kind of moving at a steady, constant rate, but they are definitely constantly changing direction, not just up and down, but left and right, inside and upside down on the Mobius strip. So there's no change in speed, but there's constant change in velocity. And these two things are definitely not the same thing. Now we also have what are called base and derived units in the metric system. There's about 7 of them that we pay a lot of attention to, and the 3 in this course that are very important is the kilogram, which is a base unit of mass, the meter, which is the base unit of distance, length, how far something is displaced, and the second, which is the base unit of time. These units we're going to use quite a bit. But we also have what's called derived units, and we derive them, that is, we make them by using the base units in different combinations. That's what we mean when we say we derive it. So as an example, suppose we cover 8 meters of distance, d, in 2 seconds of time, t. We derive the unit of velocity from the 2 base units, and thus we get a vector that has both magnitude and direction. A vector with both magnitude and direction. So the formula is velocity equals delta d over delta t. Now it looks really scary and fancy math, but it's not. Delta d just means a change in distance, a change in displacement, and that'll be measured in meters. And delta t, as you might imagine, just means a change in time, and we're going to measure that in seconds. So if we have 8 meters and we divide it by 2 seconds, we can do that math in our heads. 8 divided by 2, yes, it's 4. 4 what? 4 meters a second. It's really that easy. Velocity is just taking two numbers and dividing one by the other. Now, of course, the curling stone doesn't start out moving on its own. It starts out at rest. And if we're going to move that curling stone, that means we're going to take it from a position where it's at rest, where it's at a velocity of 0, and we're going to have to accelerate it to some positive number. We represent acceleration with the Greek letter alpha, which kind of looks like a little fishy. And how do we calculate it? Well, pretty similarly to what we did with velocity. This time, instead of having a change in displacement, a change in distance, we're going to have a change in velocity. So acceleration is delta v divided by delta t. And of course, the change in velocity is a change in meters per second. Here, we're going from 0 to, say, 4 meters per second, like on the previous problem. And we're going to say this takes place over 2 seconds. So if we have 4 meters per second, the change in velocity over 2 seconds of time, guess what? We get 2 meters per second squared. An object in motion like this, like the curling stone, is said to have momentum. And just like acceleration, momentum is a vector property which is derived from velocity. The symbol here looks like the letter P, but that's the Greek letter rho. Rho equals mv, so momentum is simply the product of the mass times the velocity. Using the numbers we previously assigned for the curling stone, we've got 20 kilograms of granite in the stone, and we're moving it with velocity of 4 meters per second. So, one can kind of do this in your head. This is just multiplication. 20, 4, multiply. What do we got? Why, yes, we've got 80 kilogram per meter per second. And note, since the momentum was derived from the product of a vector and a scalar, this momentum is also a vector. It also has magnitude and direction. Now, force is also a derived term, and it's equal to the product of a scalar, which is an object's mass, and a vector, which is that object's acceleration. So we used velocity to make acceleration. Now we're going to use acceleration to make force. You see why I want to put these things together? This relationship, that force equals the product of mass and acceleration, was first proposed by Isaac Newton as one of 3 laws of motion in his landmark 1687 book, Principia Mathematica. Probably one of the 10 most important books in the history of science, maybe one of the 10 most important books ever. In this book, Newton proposes laws of motion. One of them we can neatly summarize with this expression: F equals m alpha, where F is the force, m is the mass, and alpha is the acceleration. And what's interesting about that, why it's nice to show Newton's face, is because we now use his name, the Newton, as the SI unit of force, which is derived from having the mass of 1 kilogram, accelerated 1 meter per second squared. So what would that look like with our curling stone? Well, please remember we previously estimated an acceleration of 2 meters per second squared, and we have that mass, the scalar that never changes, the 20 kilogram curling stone. So this equation is just going to be 20 kilograms times 2 meters per second squared, and we're going to get 40 of this, but that's basically 40 newtons. 1 kilogram per meter per second squared is defined as 40 newtons. And of course, since force is the product of a scalar, the mass, and a vector, acceleration, it is also a vector. Now, forces are interesting because they form part of our standard model in physics. Electromagnetism, gravity, and the strong and weak nuclear forces all appear in the standard model. And these 4 fundamental forces are described as being interactions between the particles that form matter, like the proton, and other particles that carry forces, like photons of light. These interactions transfer energy and momenta between particles of matter. I'm going to say that again. They transfer energy and momenta between particles and matter. So now we finally reach energy, and you see that we have our scalar is that we have work / energy, like we're treating work and energy like they're the same thing. More on that in a moment. That's in blue, and that is a scalar, which is surprising. And then our force is a vector. So energy is a derived term. And just as we derive force from mass and acceleration, we derived acceleration from velocity, and we derived velocity from the base units of the meter and the second, we're going to derive energy from force. And surprisingly, even though both scalars and vectors can be involved in calculating force, they can be involved in calculating energy. And even though there's a lot of different ways to calculate energy, surprisingly, the resulting number in joules is always a scalar. The energy is never going in any one particular direction on its own. It's simply a stuff. Energy can be hard to define because it does take so many forms. And it can be converted from one form to another to do so many different things. And so we posed this question previously. There's two different sources of energy shown in this picture with two different forms. And what are they? You might speculate. Energy can be generally defined as the capacity to do work on a system or to produce heat, which is typically lost by the system. Energy can be generally defined as the capacity to do work on a system or to produce heat, which is typically transferred or lost by the system. Suppose this car is being driven down the road. What work done on the system moves the car down the road? It would be interesting if you could tell me what sort of ways heat could be lost by this system. Again, I think this is real world everyday experience. You know things about cars from your senses. You probably can tell me ways in which the car is losing heat. Now, the concept of work which is being done on the system allows us to relate the idea of how forces are able to transfer energy. We call this idea the work-energy theorem. So one thing we can say is that work, W, can be defined as the product of a force and the displacement in meters over which that force is applied. So you have an amount, a vector, which is the force, and we also have a meter, a displacement, which is also a vector. And the product of two vectors, in this case, is going to be a scalar. But notice that this is just multiplication. It's the force in newtons times some displacement in meters. And we can get work out of that. And work is essentially equivalent, functionally equivalent to the energy used to do the work. The net work that's done on that system is equivalent to the change in that system's kinetic energy, here shown as delta KE. So that means that force times displacement equals the change in kinetic energy. And so if you're careful, if you're thoughtful with the work-energy theorem, and you use different parts of it, you can see how forces manifest themselves and lead to energy doing things in the real world, either work on a system or the loss of heat by that system. Now, the energy that's stored within a system is called potential energy. Here we've got someone stretching a rubber band. That's a form of stored energy. As long as you're stretching it, you're putting energy into the system. If we were to relax our fingers, the rubber band may fly off, and much of the potential energy stored in stretching the rubber band is instantly converted into kinetic energy. Now, the dual nature of energy can be clearly shown by looking at how gravitational potential energy is converted into kinetic energy. So here we have a boulder, and the boulder's at the top of a cliff and it's leaning over. It looks kind of dangerous, kind of scary, like something's going to happen in a given moment, you know? This boulder has gravitational potential energy. We know if it moves and it falls, it could do some damage. And this energy is proportional to the mass of the boulder, its height above the ground, and the acceleration due to gravity. So the mass is 100 kilograms. We estimate the height to be about 8 meters, and the acceleration due to gravity, roughly 10 meters per second squared. So our potential energy equals mgh, the mass times the gravitational value times the height in meters. That's 100 kilograms times 10 meters per second squared, and in this case times 3.2 meters. Times 3.2 meters. The result of this calculation, 100 times 10 is 1,000, 1,000 times 3.2 is 3,200, and our unit for energy is joules. So this is 3,200 joules. But now the boulder is going to do its business. It falls. Calamity. As it falls, it reaches an average velocity of 8 meters per second. As it falls, that potential energy that was previously stored is now being converted into kinetic energy, the energy of motion. If the boulder falls, it converts that potential energy into that kinetic energy, and that is said to be the product of the mass, m, and the square of the velocity, v squared. We say 1/2 because we're taking the average over a period of time, 1/2 mv squared, and that's going to be 100 kilograms times 8 meters per second squared divided by 2. And what do you know? 8 squared is 64 times 100 is 6,400, the whole thing divided by 2, and it's 3,200 joules. The amount of kinetic energy after is exactly equal to the amount of potential energy before. Another example of way kinetic potential energy can be converted is with the pendulum. As the pendulum moves back and forth, there are moments where it's not actually moving very fast at all when it reaches the peak of the curve it's describing on either side. And then there are moments where its velocity, its kinetic energy is at a maximum right beneath the fulcrum straight down. And so as it moves back and forth, the pendulum takes turns storing energy and releasing energy. And the moments where kinetic energy is dominant is highlighted in red. The moments where potential energy is dominant is blue. And a similar phenomenon is shown in the background with the Newton's cradle, with the little metal spheres, coming into contact and transferring energy and so forth. Well, what both the pendulum and Newton's cradle have in common is that they're a little bit more realistic than the simple example of the boulder falling, because it considers what happens if you try to make this process of exchange go back and forward indefinitely. The boulder only falls once, well, pretty much all its potential energy gets converted into kinetic energy. But if you have a system like this where you're going back and forth, gradually what happens is the system loses energy, and it actually loses energy in the form of heat. We look carefully, we see a growing yellow line, which is labeled friction. And this is due to the, resistance of the air, the stretching back and forth of the string holding the pendulum. There's a little bit of heat being lost in all that. And as energy is lost with each swing, gradually the pendulum will start to slow down if left to its own devices. To keep it swinging back and forth, the experimenter would have to put a little bit more energy back in. But this is the idea. Energy is based on force. Force is based on acceleration. Acceleration is based upon velocity. And all of these derived units are somehow made from base units like the kilogram of mass, the length of the meter, and the time of the second. And so it's kind of nice to see that these three simple units that are base units can be used to do so many marvelous things and talk about so many great concepts, and allow us to do all kinds of measurements in science. That's a pretty cool thing.